Dark matter can accumulate in dead stars. We still know very little about it, and yet it is at the center of many of our ideas about the structure of the universe. It's dark matter. In new research, scientists suggest that dark matter may accumulate in the very dense interiors of neutron stars. According to the standard cosmological model, the universe is filled with much more dark matter than baryonic matter, the normal matter we know. This hypothetical substance is invisible, does not emit or reflect light, and is therefore very difficult to detect. Despite years of research, the existence of dark matter has not been confirmed. Scientists are still trying to figure out what its exact nature is and what creates it. In new research, scientists suggest that dark matter may be accumulating in neutron stars. Neutron stars are incredibly dense objects that form after the supernova explosion of a massive star. They are among the densest objects in the universe and second only to black holes in this respect. Researchers often use a fairly explicit comparison. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. The atoms inside a neutron star are so tightly bound together that they behave in a way that is not found anywhere else. Dark matter cannot be directly observed. We do not know whether it is a still unknown type of particles, or waves traveling through space. However, it is believed to be present throughout the universe. The only thing we have to confirm that dark matter really exists is various kinds of indirect evidence. Its existence is betrayed by its gravitational effects. At least this is how scientists explain anomalies in the rotation of galaxies and the movement of galaxies in clusters. There is too little visible matter to explain the effects in these cases. However, one thing about dark matter seems to be known. It must have gravitational forces, and therefore we would expect its presence, especially where there are strong gravitational fields. Black holes would therefore be a natural suspect, but for obvious reasons, we would not be able to study the dark matter accumulated there. Scientists have looked for a slightly easier target: stellar remnants, such as neutron stars. They are incredibly dense. Compared to the Earth, it is 100 trillion times denser. No wonder that they have an extremely strong gravitational field, which is even able to make light circulate around them. And it is around neutron stars that dark matter could also be found, or inside them. In particular, her potential impact on such a star would be interesting. For example, its particles interacting with each other could sometimes lead to the release of a certain amount of energy. However, with an unusually high concentration of dark matter in this place, we could expect that such an accumulation of energy and heat could occur in this way. which would be able to affect the internal dynamics of such stars. If particles of accumulated dark matter collide with normal, under the above circumstances, energy can also accumulate in the star itself. This in turn, thus heating the star to extreme levels, can trigger a runaway nuclear chain reaction. Ultimately, it can cause a superburst, detonate a star, physically annihilating it. If dark matter accumulates in its core, steadily increasing its mass, it may in turn cause an implosion that turns the star into a black hole, engulfing what is left of the star. The description and results of the research will soon be published in the journal Physics Reports, and are currently available in the arXiv preprint database. There may be another planet in the Solar System. Two astrophysicists have found an explanation for the unusual way objects move in the Kuiper belt. Scientists believe that the cause is an unknown, mysterious planet that may be the size of Earth. Finding planets is not an easy task at all. For example, Jupiter is huge and relatively close to us, so we have known about its existence for a long time. Likewise, other nearby celestial bodies. We can also detect exoplanets. Over 5,500 have been detected so far, located outside the Solar System. However, it turns out that discovering planets in our immediate neighborhood is much more complicated. An example is the Kuiper belt, also called the Edgeworth-Kuiper belt. This is a huge area extending beyond the orbit of Neptune. It contains many small objects that are remnants of the formation of the Solar System. It is home to at least 3 dwarf planets, Pluto, Haumea and Makemake. To discover larger objects in the Kuiper belt, you must first determine where they may be located. The easiest way to do this is to observe the movement of other celestial bodies. For example, the existence of Neptune was predicted by the mathematician Urbain Leverrier, who noticed that the orbit of Uranus ran contrary to the laws predicted by Newtonian physics. He then calculated that the orbital pattern could be explained by the gravitational influence of another planet. He was right. When the German astronomer Johann Gottfried Galle checked where, according to Leverrier, the new celestial body should be located, he found Neptune. Now, similar calculations have been made by 2 scientists from Japan. Patrick Sophia Lykorka from Kindai University and Takashi Ito from the National Astronomical Observatory. Researchers looked at the movement of objects in the Kuiper belt. By conducting simulations, they determined that the unusual movements of objects located far beyond Neptune's orbit can be explained by the existence of a large planet there. According to experts, the new celestial body is approximately 1.5 to 3 times larger than Earth. The article makes suggestions on where to look next. The object should be about 150 astronomical units. Astronomical units. 1 astronomical unit is equal to our planet's average distance from the Sun, approximately 150 million kilometers, from our star. More detailed knowledge of the structure of the Kuiper belt may reveal or rule out the existence of a hypothetical planet in the outer solar system, the scientists emphasize. The description and results of the calculations were published in the Astronomical Journal. Scientists managed to slow down the chemical reaction. We know that many chemical processes occur at such a fast pace that they cannot be observed with the human eye. Ideally, it would be possible to slow down such a process and take a closer look at it. Recent research shows that it is possible. Australian scientists have used a quantum computer to design and directly observe a process critical to chemical reactions, slowing it down 100 billion times. It is by understanding the basic processes occurring inside and between molecules that we can open up a whole world of new possibilities in materials science. Drug design or solar energy harvesting, said Vanessa Olea Agadello, co-author of the publication, which appeared in the journal Nature Chemistry. Under natural conditions, making this type of observation would be impossible. In the specific case analyzed by the researchers, the reaction time would be measured in just femtoseconds, which is 1/1,000,000th of a second. But researchers from the University of Sydney managed to slow down this process by as much as 100 billion times. Its duration was extended from femtoseconds to milliseconds. And all this became possible thanks to the use of a quantum computer, which created a system that allows for slowing down the dynamics of such processes. In Sydney itself, there is the best quantum computer in Australia, which allows carrying out this type of experiments. The research team observed a single atom interference pattern caused by a geometric structure common in chemistry called a conic intersection. They are crucial for rapidly occurring photochemical processes. Examples include human vision and photosynthesis. How these processes take place has puzzled scientists for a long time. Observing their dynamics had been on their wish list since the 1950s. But for obvious reasons it was not possible at that time. The key to making this enormous progress was a quantum computer, specifically one using trapped ion technology. In this way, the entire process was reproduced and mapped on a very small quantum device and then significantly slowed it down. As the co-author of the publication, Dr. Christoph Valahoo, comments, "The method used is in a sense reminiscent of simulations of air movement around the wing in a wind tunnel. The most important thing is that in this way we did not obtain only a digital estimate, a digital version of the process, which could then be analyzed. Our experiment was not a digital approximation of the process. It was a direct, analog observation of quantum dynamics, Vallejo said. Needless to say, this groundbreaking research will open up completely new possibilities for us in the field of materials engineering and drug production. However, this is not the end. Because thanks to them we can better understand how smog is created or the ozone layer is depleted. In general, it will be possible to observe ultra-fast dynamics in which molecules undergo changes in an extremely short time.